You've seen it, right? In just the last few years, AI has absolutely exploded with capabilities that feel, well, they feel like magic. One minute it's writing a poem, the next it's churning out computer code. But what if I told you that this incredible, world-changing progress isn't magic at all? What if it's actually following a predictable, almost physical law? That's exactly what we're going to unpack today.
So that's the big question. Is this whole AI boom just a series of random lucky breakthroughs? Or is there something deeper going on? Something we can actually understand and maybe even predict? Is it art or is it engineering? We're going to get to the bottom of this.
And the answer, it turns out, lies in this fascinating concept called scaling laws. Honestly, the best way to wrap your head around them is to think of them as the laws of thermodynamics for AI. Seriously, just like thermodynamics tells us how energy and heat behave in a system, scaling laws reveal how intelligence emerges when we pour resources into these models. It's the science that connects what we put in.
All right, so to really get this, we need to pop the hood and look at what's actually going on. Let's start with the fundamental engine that's driving all of this incredible growth.
Here's the most crucial takeaway right up front. We are witnessing a huge shift. For years, building better AI felt like an art form, a series of clever tricks and happy accidents. But scaling laws are turning it into a disciplined science, an engineering practice, where you can actually calculate and plan for the outcomes.
So if AI development is becoming a real science, what are its fundamental elements? Its atoms, if you will. Well, it turns out it really just boils down to three key ingredients.
First up, we've got compute. This is the raw horsepower, the sheer processing power from thousands of computer chips grinding away for months. The source material has this brilliant description for it, calling it the kinetic energy of the system. It's the work, the energy being put in to make all the learning happen.
Next, you need fuel for that engine. That's data. We're talking trillions of words, countless images, and endless lines of code that the model gets to learn from. Think of it like a giant library that the AI reads to understand our world. This is the informational energy that gets converted into intelligence.
And finally, the third piece of the puzzle, model parameters. Now, this one sounds a little technical, but it's basically just a stand-in for the model's size and complexity. Think of it as the number of knobs and dials inside the machine. The simplest way to put it, it's the model's brain capacity. A bigger brain can learn more, right?
Okay, so we have our three ingredients: the raw power of compute, the fuel of data, and the brain capacity of the model. But how do they all work together? This brings us to the mathematical heart of it all, the predictable power law.
This is where researchers had their minds blown. They discovered that when you increase these ingredients, the model's performance doesn't just get better randomly. It gets better along a smooth, predictable curve. The number of mistakes it makes, what researchers call loss, goes down in a way you can literally plot on a graph and forecast.
And this is the law itself. Now, don't let the letters and symbols freak you out. All this formula is really saying is that the model's error, that's the L, goes down as you add more resources, that's the N. That's it. It's an elegant and almost shockingly simple relationship that governs these incredibly complex systems.
But, and this is a huge but, you can't just throw more of one thing at the problem and hope for the best. There's an optimal recipe. As you can see here, if you want to make your model's brain bigger, you have to give it proportionally more data to learn from. It's a balancing act to get the best results without wasting a ton of energy and money. And this is where things get truly mind-bending. Because this smooth, predictable improvement, this simple increase in quantity, leads to something completely unexpected, a radical jump in quality. This slide just says it all. The expectation, on the left, is that a bigger model would just be a little bit better at the same old tasks. But that's not what happens. The reality is on the right. At certain thresholds, at certain sizes, models suddenly gain entirely new abilities, things like reasoning or multi-step problem solving. Skills they were never ever directly trained to do. They just emerge.
The best analogy for this, by far, comes from physics. It's like a phase transition. You could slowly cool down water, 1 degree at a time. That's your smooth, quantitative change. But then, at 0 degrees Celsius, bam! It's not water anymore. It undergoes a total qualitative change and becomes something completely different, ice. In the exact same way, just by adding more data and compute, these models suddenly crystallize new, more complex abilities.
And this revolutionary idea has a name: the scaling hypothesis. This is the core philosophy that is driving the entire AI industry right now.
It's the belief that we might not even need a magical new algorithm to get more general intelligence. Maybe we just need to keep scaling up what we already have.
So if this hypothesis is true and progress is really this predictable, what does that let us see about the future?
Of course, this can't go on forever. Just like any physical law, scaling has its limits. You can see it in the curve. Eventually, you're going to start seeing diminishing returns. You might run out of high-quality data on the internet, or you just physically hit the limits of how many computer chips you can build and power. This explosive growth will eventually start to flatten out.
But here's the most powerful takeaway of this whole thing. Because this process is governed by predictable laws, it means we can actually forecast the future. Researchers can run tests on smaller models, plot that curve, and then predict with stunning accuracy how a model 100 times bigger will perform before they spend the hundreds of millions of dollars to build it. AI development is no longer a shot in the dark. It is now a predictive science.
And so that leaves us with this one final, really profound question. For centuries, we've thought of intelligence as something mysterious, almost spiritual, or at least uniquely biological. But now we have hard evidence that at least some of its key properties follow these simple, predictable, physical-like laws. So, if intelligence can be engineered, if its growth can be plotted on a graph, what exactly are we scaling towards?